So, today, we're looking at gold, right? So, are you all, if everything works perfectly, ignoring your experiences on Monday, would you expect to see single atoms today? You have a yes? What do the rest of you expect?
I don't know, because I thought we were trying to just look at like induction, and I didn't.
I'm not sure.
So, the truth of the matter is no. This STM is not fancy enough for single atoms of gold. If we had ultra high vacuum and ultra chilled, we could. But I'm going to explain to you guys why. So this is a gold atom, right? What set of orbitals is my valence shell? D orbitals, exactly. Now, you have to forgive me, I can't really draw D orbitals that well. I'll do what I can. I'm not even going to draw all of them because, as I'm sure you all know, that makes a mess. Someone said the same thing last semester. So this is some of the D orbitals, right? Time is up. No, not allowed. You didn't pay the toll.
What's the password?
Now, take this orbital drawing and put it on these other ones. All right? That's a lot. And we've also got, overlap going on between all of these, right? So imagine, if you will, that I completely oxidized these gold atoms. I took out every single D electron in the valence shell, okay? Now, I'm going to take one electron and put it back into the system. Where is that electron?
So do you mean that you're taking out one electron from D orbital?
No. We've already emptied the D orbitals.
Okay.
I have one electron, and I am putting that one electron back in after removing all of the electrons. Where is it? Where on this drawing?
In the middle? The higher? What do y'all think? If you put it on the high, wouldn't it go to the lower ones?
You would like it to be in the lowest possible
Where in
energy
space?
state. Where in space? How do you even answer a question like that?
Like this. That's where it is.
So it's anywhere.
It's everywhere.
Yeah.
Not anywhere, everywhere. It's delocalized, right?
Yeah.
Now, I'm going to put in another one. Where is it? I'm going to put in another one. I'm going to put in another one.
It's on the right side.
Right? And there's a lot of these things because gold has a lot of valence electrons. So this produces an effect that's known as a sea of electrons, sea like body of water. So what happens when we put an STM tip over this is it sees this.
That's very
Instead
good.
of seeing this. What we should see with the straight gold is just a smear. It should look like crap. Yours does not look like crap. That's why yours is wrong. I'll get a little bit more into that in a little bit. So, if you compare this to the HOPG, where you can fairly easily and readily get the atomic resolution, what's our valence orbital? Graphite. Carbon. P, exactly. Bam. Atomic resolution. Right? It's pretty readily localized. Versus this one where you have to really cool it down to localize those electrons and be able to STM to the point where you can see it. And we don't have the capability to do that on this system. Oh, it came out of tunneling range. Oh well, we'll get it. Now, what would happen if I was to take these gold atoms again and Exactly. I'm going to put the alkane thiol monolayer on there. I made these two soluble ones. I shrank them down so that I could draw them up. So, I put this monolayer on there. What does that do to the surface conductivity? It insulates it. Exactly. Because these are saturated, you know, it's not very easy to tunnel through that, it's just a thicker barrier.
So the increased saturation makes it more insulated, right?
Yes.
Okay.
Now, what do you think this will do to the imaging quality?
You can see one.
Sorry?
I don't know if you can see one, but maybe the point would make it. You can see one.
We're still not going to be able to see one atom.
But you can. The points are maybe more specific.
So, when regular gold is working properly, you shouldn't be able to discern anything. It'll just be wash. However, we do this, we actually get really clean pictures typically, and you can see the nice terraces and everything. Because instead of our sea of electrons, we've now done this. We've localized them so that we can put our tip over and it will see that point. You know, it'll do that for all of these. And that cleans up the pictures dramatically, even though it doesn't conduct as well as just pure gold. Does it make sense why that happens? All right. Now, what would happen if I were to do this?
I'm sorry, what?
Those are double bonds.
Yeah.
You're going to get resonance over here, so because of the pi bonding you have.
Okay, it increases the tunneling, and that's actually pretty much the most important thing of this. So if I now scan over this, you were right when you said resonance. You get better tunneling through those double bonds up to your tip. Now, why do we care? We're not putting multi-ene thiols on there. This concept, although typically not done with polyene thiols, is known as a molecular wire. And these are, it's typically done with something like a paraffin or a stilbene, some big conjugated thing. But you can put it on there with an alkane thiol solution, and it will get stabilized in the monolayer. And as you're scanning across, the conductivity is so much better, it just lights up. Remember when I had you guys plot the topography thing?
Yeah.
That's the equivalent of a green region in that map. It'll show a spike. And so you can pick these molecules out in a monolayer really easily, sit the tip on them, and do all sorts of electronic studies of them. We're not doing them in here, but that's one of the things that they do in the field.
Okay. My question is, if all of those had double bonds, would it look like less clear? Because wouldn't the double bonds, what Andy was saying, increase insulation? Or decrease?
It would make it more conductive, but it's still localized. I don't know with 100% certainty,
Okay.
because as far as I know, no one's done that. You don't typically do it with polyene thiols.
Yeah.
And the big molecules you do it with are really big. But I would think you would still get clearer images than the pure gold, because it's still localized like this.
Okay.
It just tunnels more easily. If you look at the parameters we run this in, we've like lowered the set point, so it's expecting to detect less current. We have higher voltages and things like that. You would go the other direction, would be my yes on that. Any questions about this? No? All right. So the reason, as I said, the fact that you had a nice clear image was bad. That means you've got something on your surface. We've been trying to solve this problem for a while now. When you go in and take the spectra of this, The range we tell you to do is negative 0.2 volts to 0.2 volts. That's so you can compare it to the HOPG. If you do that range, yeah, you'll see a linear IV spectrum. But if you look at the y-axis, it's in picoamps, not nanoamps. So it's very small. And if you then change the range from negative 2 volts to 2 volts, the same range we do on the monolayer, you will see a very clear sigmoid curve. That's further evidence something's wrong here. Gold is a conductor, a pretty darn good one. I mean, there's probably some gold in the electronics in that phone you're holding up. So this is further evidence. When you're doing the analysis for this experiment, take the linear one and do your mathematical analysis, your calculations of things with that one. But also report the other one, the sigmoid one that we're in all likelihood going to get to prove this is a reason our numbers don't necessarily agree. All right? Any questions? Concerns? News? All right, carry on.
That's good. Thank you.